degree, they asked me to start with simulation. So I validate not Gen 4 because at the end of my my doctor degree, because of problems with the code they asked me to work with, I started working Gen 4. It was 2004, more or less. Okay, and then I use ITS Tiger series that is made only most for neutrons and secondary particles from that in reactors. I work with MCNP that today has very good, but in my time it was the 4B. That's a nightmare for people who used to work with cubes, because the cube is not a cube. The cube is an interface of different six different surfaces. So it's a nightmare to describe more than one cube in your universe. And I will explain you later why it's so complicated. And then in 2004, I decided to, because I changed it 4 times. And you know that for code, for the Monte Carlo code, so I need to tell you that because every time I need to move to another one is like a breakup with a boyfriend. It was very complicated because you spend a lot of time understanding the tool, learning how to communicate with the tool. So get very excited at the beginning, then you get very upset with the problems, and you know how to solve the problems, and then when you finish in a very good way, and you need to move to another one. So it's complicated. So I decided to go to a tool that's more complete and make me possible to study different areas of the physics. So that's why the main idea. Okay, today should be only for accelerator physics, but talking to the people here and talking to Bertrand, we decided to make something a little, because most of people didn't use Gen 4. Is that correct? Or no? Okay, and you need to talk to me because it's going to be something like this, okay? And so before we start to run the examples and jump in the depth of the horror of using Gen 4 without knowing what we're doing, you need to understand the basic stuff in Gen 4. Here we're going to scratch a little bit the surface, nothing more than that, okay? So if I'm using, remind, I am from medical physics, I work with programming in C++, and people from biology think that I am physicist. So my language is a little bit different, okay? Because I was learning and changing of area in different moments. So if I say something you don't understand, please stop and ask me, because it's important. It's the basic language in Gen 4 that we are using now, okay? Some stuff are going to serve to any kind of Monte Carlo toolkit. So some are very particular to Gen 4. So let's start. So I put the objectives here. So today, I hope we can define. You should know what Gen 4 is, and we can use it for what, okay? So for people say Gen 4 code, Gen 4 software. Gen 4 is not a code, it's not a software, it's a toolkit. It's a group of classes, okay? A program is more elaborated, and then, so no, Gen 4 is a toolkit, okay? So we try to understand a little bit how Gen 4 starts at the beginning of our lecture, okay? Make an overview of main architecture and components, and the key concepts for geometry. Do you know that the coding program, the elegance of coding program, has one law that we call encapsulated law of programming? It's not like that, it's a little bit different, but the main, you know that? Saying that one part of the code cannot change. If you change one part of the code, you cannot mess up the other one. So Gen 4 has a very restricted way of programming. So geometry is something, physics is something you can change, but you can change in physics, could not change the results in geometry, okay? And this is very important because this is a way you can take different pieces of the code and test it to see how how things are going and flowing. Then we will explore a little bit the applications. These different kinds of applications, and talk about a little bit the limitations of that, because Gen 4 is huge, but it's not tested for everything. So if you have something special for you, you should test your tools in the different levels. So we're talking a little bit about that. Understand basic limitations, and run some examples at the end, and understand the classes and where things are in Gen 4 applications. When I talk Gen 4 applications, Do you have any idea what I'm talking about? Or not? Okay, application, developer application, is the guy who develops something for a specific experiment. So we're going to take the physics available in Gen 4 and all the tool, and you try to do your best to simulate the realistic experiment. So it has a lot of levels. So here, most of people here are going to work with developer application. I do that for 20-something years. Forget about the something, okay? 20-something years. So it doesn't mean that you need to know everything about coding. It doesn't mean that you need to know, of course, you need to know a little bit of C++, but it doesn't mean that you need to know extremely internal details of the programming, but you need to understand the physics behind that. One of the most common problems and errors that people think is everything is already done in Gen 4. Everything is validated in Gen 4. No. We have validated for the big experiment stuff, but it's important we see the reliability of our data, of our geometry. And for do that, we have, I can tell you about that, some tasks that you can do during the development of your application. So that's the thing. The application and create a group of classes that are going to see realistically an experiment. If I'm doing too slow, or if it's too simple for you, please just let me know that I can change it, okay? I put some, where I can find information about Gen 4. Manuals, and then you have specific manuals that the people who are going to develop an application, okay, when find information, I love this one, but you have how to install it, and then you have write an application, and then you have frequent question asks, and furthermore. Here, you have 3 different models, 2 different manuals. One practical information for you. If you wanted to work with Gen 4, forget about read the complete manual and understand everything. I'm studying that for 20-something years and I'm still learning. So it's too much things. So take one thing, one condition that you'd like to study and study for that. And then you are going to evolve in this kind of things, okay? So you have here physics reference manual. It's important to read because one of the most common problems I can find in the people is, say, for example, for low energy. Oh, I'm using the liver mode model in Gen 4. Great. And I compare that with PDL. And it's the same. Of course it's the same. Because the cross-section liver mode based on PDL. So if you get something different, they did something wrong in the implementation. So when you talk about simulate something, you need to understand the cross-sections and the models that are going to be applying behind it. You don't need to understand completely the implementation, but you need to know what cross-sections are, okay, and the things that are behind. So you can assume some systematics of your model in the simulation. Okay, this is something that you cannot talk too much because it takes a lot of time to, to explore, but you need to be aware of that. Then you have the physics list guidance and toolkit guidance developer. Okay, the physics list are going to talk later because Gen 4, differently of other specific toolkits, it's a generic one. So do you know what generic toolkit in Monte Carlo means? Okay, you have a class of Monte Carlo toolkits that are specific. They are made to simulate, for example, photons interacting to something that is a specific material or in a specific geometry. So then you can do it faster because it's dedicated, it can jump some sub-steps, okay? But Gen 4 is a generic toolkit. For assumption, we don't know exactly what the user is going to use for. So we try to do it more detailed as possible. So in this case, we have different physics lists because different experiments are using different particles in different energies and different models fits best for that experiment. So when you use Gen 4, everybody in the beginning quite very excited to do, oh, I'm going to do the best geometry. Forget about the geometry. You have physics behind that. Geometry is one part that you can add at the end. but you need to have something here. So you need to have the space, you need to have the material, okay? But the details in the geometry, you can do that later. You need to be sure that your physics is good enough. And if you complicate too much your simulation, you cannot test that. So what you should do is make simple the geometry, and then test the energy and the particles to check if your physics list is the best one or if you need to change something. For another physics list, I don't ask you, please don't try to change the physics list in the first time, because I had a student that got he created actually a positron in 60 kV because he decided to do it faster to run the Gent 4, and then he screwed up the physics list. It was running faster, but it was really a mess. So, but you have different physics lists to choose, so you can make your choice in the best way. And we are going to discuss how Gent 4 can do that. So after you test the main geometry, after you test the physics you have in simple experiments, and you can see your geometry and your physics is reliable, then you can complicate a lot your geometry. The only thing you need to know is that big experiments already have the geometry for you done, so you just need to import. And if you're going to create your own files in GDML or CAD or any other kind of mesh structure, like tetraedros coding, you need to be sure that you don't have holes on it. Because for any Monte Carlo code, the most problem it was in MCNP4B is what is inside and what is outside. If I don't have this description, if my mesh structure is missing one, is open here, then if I get some particle coming here, it gets lost. It can crash out in a segmentation fault, or it can in an infinite looping. Okay? So you need to be careful about how to describe your geometry. And don't think too much and stress out with the geometry. Because if you have the best geometry, but if you use a material that is based in Gent 4 has a list of materials to import. Okay? If it's a pure material, high purity material, good, you can use that. But leagues are different. Aluminiums, lead, and other stuff. So you need to describe yourself for that, because otherwise you're going to have different impurities in different regions of the country, and then you don't get the proper result. So before you think about geometry, think about the composition of the materials that you are using and the other things that you're using Gent 4. We're going to talk about that several times, okay? But I think it's a good message in the beginning. Do you have any question? Yeah? Ah, come on. You can talk?
Okay. You can talk about the main difference between, for example, Gen 4 and the multiphysics, because I never worked with Gen 4, and you are talking, remember me a little bit of the multiphysics, the console. And you can talk about the main difference.
I don't know very much about multiphysics, okay? But what I know that multiphysics is a generic toolkit, again, so, but it has different models and processes implemented, okay? And the way of communicate is a little bit different. If I remember multiphysics, you need to implement a little bit of physics together in some moments. Here in Gen 4, you don't know that, you don't do that. Unless you wanted to introduce a exotic physics in the middle. Then you need to, and then we're going to talk today where I can introduce my physics, where I can get the information from Gen 4. This is very important. I don't know if it's okay. So the difference main is that Gen 4 has, I think, and the moment that I knew multiphysics, I don't know if I've evolved too much now, but Gen 4 has more models to each process. And you don't need to implement all the physics. In multiphysics, you need to implement something. Okay? Okay? Huh? Both. Okay, multiphysics. Okay, now it's not open source because I was using, I don't know if it was. I'm sorry. When I use it, it's in the group, it was an open source tool, so I don't know. Now it's not. I'm sorry.
Gen 4 is free. Multiphysics is paid. It's necessary to pay for.
Yeah, I didn't know because I use it like free. So probably my institution has it and developed like a free. Thank you very much. It's completely free, but the problem is, I know it's not a problem, but we have updates every 6 months in Gen 4. So be careful when you do your improvement to the new physics. If you have something very sensitive, it's nice to have your own validation tests that you can do in your application. Because sometimes it's a huge tool. It can have some bugs. Doesn't mean that it has some bugs, but any large tool like this, you can have some bugs. Okay? So you need to be careful about that. Any question? So we are talking now about a little bit of, oh, come on. Só pouco. Just a second. Come on. So let's go. So we can talk a little bit about the characteristics of Gen 4. It's an open source, okay, oriented object toolkit. It gives you a lot of advantage because, or not, or not. If you are careful to deal with Gen 4, you can get a very nice simulations, but you can screw it up if you don't think what you're doing. So that's the problem in an open source tool, okay? So you have, it provides components needed to build a wide range of simulations. You have almost a great number of particles, even the photons, gamma, muons, hadrons, blah, 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 and you go, wide. And you have wide range of energy. The details models like Livermore for electromagnetic fields, like Livermore and Penelope, we can go until 250 kV. I'm sorry, 99 kV. To standard models, 250 kV. So you can go down. And if you need to go down, you can use Gen4 DNA. But Gen4 DNA has one thing is different. It's difficult to find a way to validate against experimental data, the models. So you need to be careful when you choose your physics list, because most of them have spill data that are, and the other are modeled by models that are not validated yet. Just that. But I use Gen4 DNA. I've always had something nice. So you just need to be careful what you're going to choose. Then you have the flexibility system to describe complex detectors and geometry. Yeah, but not so. Since I have worked in the last years, I saw that people have some problems to talk to Gen4 because people are not get used to programming C++. And Gen4 is a C++ programming tool. But you have Python interface, and you have several frameworks that you can use depending on your application. Okay. When I talk that you have a framework, do you understand what I'm talking about? Yes, no, maybe, no. Okay. Framework, in a gross way to say, it's an interface that you have to talk to the code. So you can put, because what Gen4 simulates? Physics, interaction. What? Interaction of particles through a homogeneous material using the independent atomic theory. So if you wanted to have two photons colliding, you cannot do that with Gen4. So you need to have another tool that you do that and communicate the result of that to Gen4. So when I put here 3 slides just with different framework for you at the end, okay? But in Gen4, you can basically, it was made in the beginning to simulate particles interacting through matter, okay, in a homogeneous way. Then you can create different situations, and you can create realistic non-homogeneities, okay? It's possible. So in the standard Gen4, for example, if I am simulated one detector here, okay, and I have a flux, and this detector will have all the electronics and amplification stuff, okay? What Gen4 can simulate? When you have a beam that's entering in the detector, Gen4 can simulate this incoming beam and all the physics, if you describe it well, the detector. But all the electronic things, Gen4 cannot do. We need to do the digitization that they call to simulate a lot of different things, including the efficiency. For example, if I have, it's not much for your area, but if I have a Geiger-Müller to use, different Geiger-Millers has different energy, minimal energy to to measure in the real life. So you have since 9 keV until 22 keV, depending on the gas, depending on the properties, and they have different efficiency. And the calibration, since you cannot see the energy, the calibration is a little bit different because we cannot. You say that the Geiger meter has no energy dependency, what's not totally correct. So we have some systematics that you have in the idea of the detector. So when you do Gen 4, you can make the sensitive volume, that is the volume that you are collecting, all the environment of that, but the electronics, the amplification of the sign, you cannot simulate with Gen 4. Use another tool. What we usually do, okay, is create a phase space. It means we create a space, a mathematical space, a phase space, that have some characteristics, the momentum of a dynamic structure. So you have different characteristics that say how you simulation in that moment. So let's say I deposit the energy here. I have one. Okay, let's go something. If I have a detector here, and it has a wire in the middle, like a probe of the Geiger-Miller. Okay, I have here the wire that goes to the amplificator and all the electronics. So you have a gas, and you have usually a positive in the middle. It's not say always like that, but you have something positive here, and you have the negative here, and you have a gas here. Okay. Then, if you have a photon coming inside and making producing ionization here, so Gen 4 is simulating. If you have all the description here, this simulating the photon coming, crossing this wall, interacting with the R, and creating the electron and the atom with the gap. Okay, so it's going to migrate. Gen 4, in principle, doesn't make this total migration. They don't create the electrons that are created in this movement. So you can use other programs to do that. Okay, but if you want to know the total energy deposited here and then create an exit here, it depends on what you want and with precision do you want. So you can use other. What the frameworks used to do, they create a phase space. For example, I create here one pair, and then I get all the information, momentum, particles, secondary particles, position, energy, kinetic energy, total energy. So you get this information in the space phase, and you put it in another code that it create this a range of particles here. Okay, so you can continue doing that. So Gen 4 is very good, but don't do everything. So you need to know what you want, and you need to know what you wanted to get from it. Okay, so this is the beginning. You're going to see something better in the continuation. Anyone have any question? So we are talking about the geometry, physics process. Also, you have a large collection of models, electromagnetic, hadronic, optical, and decay process that we can use. And when you say large, sometimes you have, for one process, in Gen 4, we have you can activate or deactivate physical processes. So you have the physicist who has the processes, and you have different models to this process. So our physicists that are already done, they evoke the proper model for this process in a range of energy, in an energy range. Okay? So my suggestion for we are beginning, we should choose the best physics list. We're going to see some physics list process in the beginning, then you see the list of things that you have and how to choose your physics list. But it's not so easy. You don't have one physics list for all. You have different physics lists that have the sensitivity and the best modeling for some experimental circumstances. Okay? It's not so straightforward. So you have, of course, the precise, tracking. So you have the simulation for transport and interaction that has the detailed information. And it has a limit. We are going to see that. And then They put here, I don't think, but user control, highly configurable and extensible by the user. Yes, but you need to understand how to communicate in C++ if you want to do something that's a little bit different or the frameworks that you have. But you have thousands of frameworks available, so you can use that for your own advantage. Okay? But if you want to do something different, you need to understand a little bit more programming. So, performance, because now you can use it in GPUs, and you use the multi-threading already supported and is already standard installed in Gen 4, so it's easier than it used to be. And of course, it's an open source and you talk, and open source and freely available for the people who the community, scientific community. So you have the main capabilities in Gen 4. We can transport electromagnetic, bioionization, Bremsstrahlung, multi-scattering, gamma interactions, optical photons. So in the beginning of my career, I just work on this optimization of this kind of physics list. Then processing models, okay? And then you have the hadronic physics, you have elastic, inelastic, capture, and other processes. Then you have the radiative decays, optical, and some extensibles, where you can add your own models. When you do that, we show in the future, we are going to communicate by specific points in Gen 4, by giving information and retrieving information in these points. It's called vertex, okay? So you need to be careful. It's not impossible, but you can even, what we're doing here is exactly this now. So Gen 4 provide a unique, I think it's a kind of advertisement, but of course, a unique combination of accuracy, flexibility, and performance. Wide choice of physics models and high precision transport, which means that you see that we can increase this by working with different parameters, internal parameters of the physics, support a very broad range of energies, so from EV to TeV that we already see and beyond, and is a tool for simulation, analysis, and visualization integrated. It's in a very powerful framework. A framework, okay, is most, in a gross way falando, is the most easy way to communicate by different kind of programs. The difference on a framework and you do your own application is if framework is based or is developed to some specific conditions. So you need to understand the conditions that your framework will build so you can use it in the best way. You can even change it, but you need to know your tool. Okay? Has some limitations on using a framework. I talking here a little bit about the we call ecosystem of Gen 4 because Gen 4 is not a tool made for one person, okay, and not one kind of knowledge. So usually you divide it in three main areas. We have the kind that the people that study the models, the transport models, and validate that. So you have the physics model developers. You have the source code developer, the guy who take this information, implement the models, okay, and make it the best option for precision in computational stuff, okay, precision, accuracy, and efficiency of coding. And you have the people that usually are that work with application developers. Why I'm saying that? Because each one of these people already tests something. Okay, so when you say that you have a model Gen 4, it's not based in nothing. You have people that thought about the model, the cross sections, the best way of describe the cross section, the grid energy of this cross section, so you can use the efficiency way to use that. And then it was validated. So these people work behind and is focused in physics accuracy and the validation. You have the people that are physicists, engineer, and people from the computational that use the coding developer, really. So it's something, when you talk about microscopic and microscopic validation of a code, do you know what's that? No? Okay, someone is alive yet. So microscopic validation and macroscopic validation or microscopic validation. You have, when you are concerned about if microsections is really implemented in the way it is in the reality. So I doing a test in a specific thing in Gen 4. So this is a microscopic validation. Okay? And this is important because this is touch deficiency of the code in this phase. So I can do something that's very specific, but at the end, for the macroscopic world, makes no difference. So we have people to test it. That's why it's important we test our physics, okay? Because it's made for a specific accuracy, okay? So you have the microscopic validation that tests parts of the code, usually the cross-sections, the angular distributions, and things like that, okay? Then, doing the best accuracy, we need to implement that. So the implementation is part of the code, but it's not the physics instead of that. It's a description of the model. So see if my model is okay, and see if the implementation of my model is okay, are two different things. And these are made for usually different teams. Okay, the guy here is just concerned about the physics. The guy here is concerned about implement this physics in the best way in computational. So it's coding. Okay, just to know this is different. So you cannot think that's the same thing and this kind of thing. So you have the application developers. You take all these things that are already done, and you use that to build a real detector. It means a simple one or a complex one in the best way. So we are going to use as a tool all the things they know. So we are going to know everything about programming things in Gen 4 now. But for sure, you need to know some basic stuff that are in the manual and the source code. And this is important to us to know. It's very simple. You don't want that I complicate a little bit more. Wow, are you alive? So we have a great team that's historical. I don't know even talk about. But when you talk about Gen 4, I'm going to stop and say, go some step forward and say, we have this different kind of a core in Gen 4. Important things that you have in Gen 4. So you have the describe of the geometry. Most of people are very concerned about that and forget about these things. It's very usual. I used to do that too when I started to use the Gen 4. And you have the physical processes. So like me, I start to work in the mammography. What I'm doing here is search of dark matter. Okay? So when I arrived here, the main concern I had is to study, and I'm still studying. Leticia is there, is my consulting person. So I'm studying the physics behind, the kind of experiment I need to do, the materials I'm using, the energy and particles, the flux, and all the experimental stuff. So I can try to transpose it to Gen 4. You cannot do that, and you cannot plan your application if you don't think about that before. So you're going to redo and redo and redo everything several times. So you need to know your experiment. It's very important. You are here to describe an experiment or to give a direction to an experiment, but you cannot say that we have the truth. You have models. And these models, okay, need to describe experiments. So you need to know the limitation of that. So you have the tracking. Exactly is, I call, it's not correct, but I call like the history of the particle, say in a particle that they're going to give subparticles. So you can track this in Gen 4. You have the simulation. And you have several utilities that are the different analysis tools that Gen 4 can be connected. You have the visual stuff. You have the digitization classes and other things that are coming now to make easier to the user use that. But you need to be concerned about these parts in the same level. Okay, and just to have a note, so when you talk about model developers, you have the right impact in the whole process, in the whole chain of process, if you are wrong in your model. So when you think about your physics, it's more important to learn about the physics available in Gen 4 already done for you and understand your needs and what you need to evoke or not, and then to concern about describe the geometry better, because you have something important that the physics. I used to listen to some people who used to say to me that's good to be programming Gen 4 because you don't need to know the physics behind. It's not true. You need to think a lot and talk a lot with people for experiments so you can do really um, a good description of the reality. So this is important. So the typical flow of a Gen 4 is, well, I told you, it's a tool that simulates what? Particle and material. So doesn't there are some people that say, oh, I don't want to know about these all the things. I just want the transport. Okay, but you cannot transport if your particle is not reaching anything. So the first thing you need to do is think about your problem. And thinking about the problem, as a application developer, you should think about the simplest geometry you can describe your geometry. So usually I start with something like one cube or one sphere, one orb. For example, Gen 4 has an orb and a sphere. What's the difference? An orb is a massive sphere that is just described by the radius because it doesn't have any possibility of have a hole inside. But the sphere can make the shell. So it have more parameters. What the impact is that in your simulation? If I can use an orb, I use an orb because I have less mathematical parameters to calculate in the middle. So it's going to be faster. So when I think my geometry, I just need to put things inside. I need to think what's the best way. What's going to be the entrance? What's going to be changed in the simulation, between simulations or in the simulations? So all these things should be discussed before you jump in Gen 4 application. Okay? So you describe your universe and you describe one object, could be a cylinder or something, then you have a source. Okay, if you're a beginner, you do something like that, and then you don't need to think too much about counting stuff because you can use verbosity of Gen 4 to start this. And then you just start shooting something. Gen 4 has a Giantino, that's a hypothetic particle that you use to test your geometry. That's very good. Maybe you can use that in your problem. But you shoot something. And then you try to see if you didn't build yet your sensitive volumes or you're not catching information. Gen 4 can put a lot of information for you in the verbosity. Then you can see the tracking of the particle, and you can see if your physics is more or less what you're expecting. You can see the proportion among the different processes, the kind of models, where your particle is going. You need to work with that to understand the geometry and to understand the physics. When this is okay, you can remove that. And you can put something more complicated here. Okay, if you put too much complications, it's difficult to find out the problem. It's my geometry, it's my physics, okay, it's my tracking, it's the way I get the information, I don't know. So that's why it's important to see the parts. So when you define a geometry, then you build, this is important. You need to have the geometry, your physics list, and the particle generator, primary particle generator. If you don't have it, you don't have a simulation. The rest, of course, is very important. But first you need to test if this is working properly. Then you can go and start to create the other classes inside. Okay? We can have a transportation with these three parts. Okay, but typically, of course, you simulate, you need to describe or choose a physics list and define where you're going to following your particles. Okay, because the particle that's here, for example, in this case, when this particle dies in the geometry, for any Monte Carlo general particle toolkit, it's not Gen 4, okay? It's when it's die, when I say it's die, when it's deposit the local energy and it's not in the space anymore. It does when there are different situations. When I reach my world, so I reach the borders of the world, it's gonna be completely die, okay? When I reach one volume, and I have a transportation and my secondary particle has no energy to be transported anymore, it's going to be deposited locally. So it depends of the model, but I can change it if I want. Okay? And I can create areas in my simulation if I am sure that's not going to create any systematics that I can die particles. I don't want particles who reach here can be completely disregarded, so I can get the information of the particle and I can kill it. Okay? That's the good thing on working with simulation. Our particles are well behaved most of the time. Sometimes not, but it's another thing. Usually it's like this. So you can create the records. I used to call, we have the sensitive detectors that are native for Gen 4, but they have different ways of get this information. We'll say where you can get this, okay? But you need to create, to know what you wanted to take from the simulation and know the point where you can get it. Usually in sensitive detector or native scores or in the stepping action simulation. So you have points and you can get this information. And then you can create heat files. Heat files are files that get informations about each step, each moment that I have an interaction. Or you can have the sum of energy or collectors. It's not just energy. You can collect particles, you can collect other energies. It depends on your detector that you're trying to simulate. Okay? And then, of course, you can visualize and have all these things that you have in Gen 4. So you see, I'm sorry to talk about that, but I think this is very important to you to understand how things are going in Gen 4. Otherwise, you're going to simulate and you're not going to separate the stuffs to be the proper tests for that. So the applications we have, of course, high energy physics, nuclear physics, medical physics. I already done all of those applications in all these areas. Space science, radiation protections. Now I am in other applications. I am trying to implement dark matter physics in Gen 4 with Leticia. So we are working on that. I already did something. So my question to you is, so how we can start an application in Gen 4? You can say, I'm going to start to using example. Who already used Gen 4? Okay, great. You already started running the basic example or the advanced examples? The first one that I saw that. People likes to go to the extended and advanced example instead of basics. So you did the right thing. The right thing is understand the basic examples. This is the simplest way that they are showing you what Gen 4 can do. Then you pick your own problem and go to the advanced and stuff like that. Because it doesn't matter what is the best implementation you have. Not only Gen 4, in any coding. The best implementation and the one that you can control and understand. If you don't control and understand, you can do something that you don't even know if it's right. It's right because it's right properly described, or it's right because the error is cancelled in the middle. We don't know. Okay? So it's important to know. So you start with the basic, and then you go to the other ones. And then you have several phases, like you describe the geometry, the physics, and the tracking, I told you before. Then you have the event management. So when I talk about events, you know what I'm talking about? What is one event? Huh? One event is the moment that I start shooting one particle until the end of this particle and all the secondaries. So it is the history of the particle. Okay, so you can follow it in Gen 4. You don't need it. You can use the time for do that, but you can do that for the identifications. You can have identifications in the middle of the way, so you can rebuild all the history of this particle that starts. So the event and the number of particles we are starting shooting, and each one has the beginning until the end, the number of subparticles too. Okay, this is an event. I don't know if it was clear for you. Okay. So you have run and track management. So you need to make choices in your application to use the proper way to do that. Otherwise, you're going to have extremely time consuming, or you are getting the wrong thing. One typical example is when some applications we try to get the flag for secondary particles in Gen 4. We already had it sometimes, and you realize that the heat files, the simple heat files, didn't combine with the collection we did. Because the collections, in some moments, count as secondary the primary that was changed. So it's a little bit different. Okay? So you need to be careful when you do this stuff. You need to check every time. Even if it seems to be already done, it's better be safe than sorry at the end. So we need to spend a lot of time to see if what's the wrong thing, and it took us 3 months with the guys. So you have the visualization tool. We are going to use KT, but you have several. Then you have the thing that you want. The input management of geometry, then you can use read GDML or any other kind of binaries. You can use even mesh structures that you have had or some tetraedric structures in mesh or something like that. Okay, so you have all these tools already done in Gen 4. You need to know how to communicate with them. It's not something that you don't need. And you have a lot of libraries and tools. We are going to use the OpenGL as a visualization tool with KT. Okay, that's the implementation easier to use. Okay, you have CLHAP root that is most usually for the energy for data analysis and create output files, but you have other options in Gen 4. Any question? Now I will leave it, don't worry. I know it's small, but I couldn't do it in the best way, so. Yeah?
Actually, I don't understand what you have to do with GDML.
What to do with digital? To introduce in Gen 4 a very complex geometry in a standard way. So can use the structure of data to import the geometry. Sometimes, and you need to know where you're getting this information, because sometimes you have the detector, you have the material of the detector, you have some limitations of the physics that's already compatible with the experiment you have. So you get all this information that's already read and we think it's already validated. It's a way, it's a format to import data that are more complex. So as I told you, the big experiments and the big projects already have this done. So the problem is not imported geometry, is know how to deal with this in a realistic way, understand the tool. That's the most important thing. So I made here, because I don't know if you have it. If you already have this idea, I'm not going to spend too much time. How is the tracking in a generic Monte Carlo toolkit? Okay, so I have we choose a number of events, a number of primary particles that are going to shoot. Can be monoenergetic or not, it's another thing. Then you give the first shoot, and then it starts to run. It's gonna to see this was initiated as 0 because it's starting the first shoot, and then it say, okay, I already achieved the maximum. No, so I have more events to run, so it start to run. Okay, if the variable that I created here is less than the maximum that I have, then I start an event. So I start an event. If not, I'm going to the end and I finish the simulation. But I'm sorry, I need to do that a little bit small, so I need to open it. So I start this and I create the event ID that was 0 instead event ID plus 1 in the second. So you create a number, integer number that will identify the history. If I got the Gen 4, the event ID, I will get the number of the primary that generate that, okay? The history of one particle. Then I go and I create a vertex. When I say that I create a vertex, or Gen 4 create a vertex, do you understand what I'm saying? A vertex is a point of information. I have a slide that gives all the information. You get the position, the time, the energy, the characteristics of the particle, and the momentum direction. This is the vertex. The vertex are the points that you are going to retrieve information and give information to Gen 4. It's the moment that you can communicate to Gen 4. Okay? Then you go and generate. Oops, I'm sorry. So you go to the vertex. Okay, and then you see, okay, I have this first, I start in the beginning and then I have this first step and I reach something.
Can I ask a question? So in this vertex, you can choose the time between the vertex, right? When it occurs in the vertex.
Okay.
When you generate a particle, you can choose the time that
you can track the time too.
Okay.
You can have the time. So we activate the time and you consider the time and you have detector that they need this information about synchronism of time. So like in pulse-emission tomography and some detectors of particles that you need to have the synchronism of two particles that need to reach the detector in some space of time, some
And,
period of time, I'm
and
sorry.
in the case of this photon that you said that interact in some point at your
Okay.
geometry, it generated two particles,
Okay.
two constituents, and this interaction is in a vertex or it can happen
The
between
interaction
vertices.
is the vertex.
Okay.
Not is in the vertex. Okay. The information of this interaction is the vertex information. So the vertex can happen anytime you have an interaction. And then you can extract information, or if you want to add a new physics, you can use this information to introduce the new physics in Gen 4.
Okay, so but there is a situation that the vertex is the information of the particle in that time is generated, but no interaction. Or by interaction, I mean modification of the, the particle transformation of them in other types of particles or something like that.
Yes, the secondary particles.
Okay.
We are talking about dark matter. That I would like to know. Because if it's dark matter, Gen 4 was not made to simulate dark matter. What you do when you want to simulate dark matter is to create one package that you talk to this vertex in specific moments. You introduce the information of the new particle and the new process and models that we are going to add. So we are talking to the vertex in that moment.
Yeah.
But Gen 4 generates the primaries, secondaries, and go follow this tracking of particles until they die.
Okay.
For the three reasons that you talked before.
Okay.
Okay? Yeah, it's better.
Maybe here there is a question of what we call vertex in high energy physics.
I have the next vertex here.
Okay, no, because I think working with Ricardo, that the point where we introduce the collision is what we call the vertex inside the LHC, for instance.
Yes.
And this is something which is unique at t equals 0, let's say at the collision time. But then you will from this vertex you will get a collection of particles that you will input in Gen 4.
Yes.
And each of them will have second, let's say their own vertex along the transport. And this is very important not to make a difference between these two type of vertices, in fact.
Let's have it the next slide. Okay, but we can talk about that. So then you need to see, okay, I got this step. Okay, so I have the properties of the particles here. And this, okay, it has not just one code that will do that. A lot of parts of the code that work with that. But in generic way, you have this particle properties. And then we are going to think, okay, I had this interaction. And I have several steps. I need to understand if I had an interaction here, what kind of process is happening here? This is the first question. After, what is the next step of this process? So it's going to generate one secondary, or it's going to have a difference in momentum direction or stuff like that. And then I need to calculate for these different particles each time what's going on. Okay, and then I will follow each one separated until the end. So it's a very time-consuming. That's why we have several tricks and several mathematical ways or statistical ways to reduce a little bit the time. That's why efficiency is so important in Gen 4. Okay, so then we have something that's important when you do our simulation. One important thing to know is the minimum size of step. And this is something important because some people did it wrongly. They count the number of steps inside of a volume as the number at the n of particles that are going there. No. To these statistics, you need to know how many particles are going inside your volume. Doesn't matter how much step each one gives, it's one unique particle. So that's why knowing the track of the particles is so important in Gen 4 so you can get a better statistics and a correct statistics, okay? So you determine the minimum path length and you calculate and then you perform a step. So I decided what process, I know it's boring, I decided what process is, I define the amount of process that I have, one, then I calculate the next step, I see the particles and calculate which particles, and then I give my step for this one, and after I follow the other one. So I follow each one by which one. Okay, and then finally, he asks, and after the step, he asks, is the end of the world? I finished my world? No. It's has something in between. There is a bordering, geometrical border in between. No, so I can get give my complete step or not. We'll see how to treat how Gen4 treat this one. And then, if you have geometric boundaries, then you need to recalculate some stuff because I'm going to get close for this border, but not going immediately to the border. And Gent4 has the way of treat this border in different ways. So you have several of parameters that you can define in Gent4 to be more realistic in the borders. So just this already has most of a week of studying because it's a lot of things. So we are not talking about that, but you see that you can do that. Okay. Gent4 has, for example, for electrons, we have multiple scattering. Okay, for the secondaries, it's very important for several detectors. But we are closing to the borders. The multiple scattering is not the best way to describe it. So we have single scattering for a moment as a limit of distance. And then we have several parameters that define these limits of distance. And all the way we are going to detail this electron crossing the border. So then it gets a little bit slower, the code. Okay, so we are going to see, you see if this has in the maximum number of history. If no, we go until, if it's yes, we go into the end. Okay, so that's the way.
I have a question.
Yeah.
Please. When you study simulation, mainly when you consider the material,
Okay.
it's necessary to define a mesh. A mesh is a grade that you will do this calculation. In this software, it's necessary to define a mesh or the parts of the material where you
You describe the geometry in three ways. Okay, you describe the volumes, the geometrical volumes that can be complex or not. Let's take it simple. Then you do it's the solid volume we call. Then you put a material inside that's a mixed, the homogeneous mix of material. And you describe the composition, the density. If it's a gas, you can do others with temperature and other things. Okay. Then you describe it, and then you put it somewhere. And Gent4 will calculate for you the steps and stuff that are in the model. But you can change it. You can have some communicated to make it more detailed or not. Okay, you have some, we call messengers, not native messenger in Gent4 that you can change it. Okay. The problem in Gent4 is you have a several number of models and processes, and you need to choose the best one. So this is one thing that you, the message here, I think so, is that, just a second, is that we should not be so concerned in the beginning with the geometry, because you need to think prime the physics behind, like it told me, the physics behind. So here is just the initial step. Okay, so this primary generator action, the class that you work with, this kind of things. So you need to have what? You need to have the primary position of the particle. In Gent4, you have two different types of doing that. The particle gun, that's the old one. And now you have several sources that are already well known. So you can have the generic particle source, GPS. Okay, the generic particle source, you have several codes that are already done for very standard source that you use in Gen4. If you have something extremely different, you need to use your coding in particle gun. So you have the position of the particle, the momentum direction that can change or not, okay, the kinetic energy, the global time of this particle, so you would like to see the timing. Then you have the step number, the volume and material is beginning where it's starting. Okay, you define these ones, and these ones are internal structures that have in Gen4. Okay, and you have send the process defined to each step. So this information, especially these three ones, are important in any kind of source that you are defining. The kind of particle, the kinetic energy, you have for this particle the momentum direction and the position. Okay, and it's different if you have, for example, a source that has some auto-absorption information. Okay, you need to describe this material source in your geometry, and then you put your primary linear direction inside the source. Okay, then you have the absorption of the source. So it's not in the same class. Do you have any question? Okay, so then you have processing and transport. I put here some information. So, okay, you have the initial step that you see that. And then you have the first step that you talk. So I decided what is the process. How Gen4 decided what process is? I have a slide here to show you that, okay? But then you have, we call this a vertex and this a vertex information. Okay, so Gen4 have this information and I go to the step until this information. Usually, you have the deposit energy in the pose step. If you want for a charged particle to deposit the energy in the middle, you need to do that. You need to say to Gen4 to do that. And you can do that by using the stepping action, G4 stepping action class. That says user class that you can use to exchange information with Gen4. So it's very useful for realistic detectors. So you have this one, and then you have initialize, you have the transportation. Okay, the in each step is the class that have the first moment of the step. Then you have the transportation for the pose step position. Okay, then I finish this. This is my pre-step in the next step. The pose step of order is my pre-step. So it's very important to understand where you are and what to get it. Because sometimes when you are inside a volume and when to see something that is going in this volume, you need to get the pre-step. But if you are inside and you want to see what's leaving, you need to check the borders of post-step. So you need to understand this. You have the beginning of a step is always the pre-step, and the end of the step is the post-step. Okay, and so I know it's very easy. It's too easy for you, you just let me know, okay? Because this is the basic. So you have then the transportations, actually that determines the step length, the next iteration, the geometry boundaries, and all the stuff. And then you have physics geometry, the pose step position, the calculation of the pose step, the analysis of the material, the calculation of the pose step, and then ready to the next step. Then I jump and I start everything again and again and again until I reach the end of the particle. Very tedious, huh? And vertex. I put here what is a vertex very quickly to let you know. So actually the geometrical vertex has the position and the time. Okay, this is the main vertex. And then you have the information about the parent. The parent ID is the identification of the mother particle that generates this one. So you can track the information by this. So you can reconstruct the information. If you print all the hits, all the impact moments, you can have the history of one particle until the end. Okay, but in Gen4, you have information that you can get. So the main vertex, you can have the position, time. You can get the parent ID, that's information, event ID, vertex ID, because you can communicate to this vertex, and the number of outgoing tracks that we're going to do. So this information we have this main vertex. But if you use the tracking information, you can get more information like kinetic energy, total deposit energy, total energy, and a lot of other information. Okay, so you need to understand what you're trying to get to communicate to the vertex or the proper class that will give you this information. And you have the pre and post step that you need to understand where we're going to pick this information. It's too slow for you? Too slow? So we have the Gen4 step definition, stage, and quantities. So what I did here is, we already talked to that, but I would like to make a scheme for you to understand exactly how we can define one step. So you have the pre-step, the post-step. Now we are imagining that this step is in a homogeneous material. We don't change the material. You don't have any borders, geometrical borders. When I talk about borders, I could have one volume of water with another volume of water. But if I have a geometrical border here, Gen 4 needs to calculate this. Okay, so when can I avoid these borders, unnecessary borders? It's extremely good because I don't need to do too much sub-steps inside of the geometry. So Gen 4 has some ways to get the made a mesh of different structures with the same material and uh, minimize the borders of your geometry. This is one way to do that. Okay, but if you have the pre-step, so you have the position, momentum direction, kinetic energy, global time, volume material, process, and you need to go the class for G4 step and G4 track, so you get all the information you can get. This is the more usual things. Then you calculate the next step, and he see that in the next step that he did in this angle, it's find a border or not. If it doesn't find a border, it's give the step and compute all the things for the next one. Get the energy, apply the deterministic calculations to do not violate the energy, the principle of conservation energy and momentum, and then it stops. So the things is, if you need to add a new physics in Gen 4, you need to be careful. Why? Because Gen 4 has a safe protection that always will try to avoid to violate the conservation energy in this step. Okay, and momentum. So it's already happened to me in some old implementations of Gen 4 that one specific model that's why I always run with a lot of verbosity in the beginning, because one of the models that are very precise got in a way that I got negative energy deposited in the standard model. So I say, okay, something is going wrong. So it's very nice because you can talk to the people. They are very nice to reply to you. So I sent to the responsible for the model, say, oh yeah, in this model we have a problem. We don't know why, but it's giving too much fluorescence. So it's deposit negative energy because of that, but it's okay. Then I didn't use it, but say you can, they will explain to you what's going on. Say next time it's already done. They don't have the problem anymore. But you can test this. Because sometimes for small energies or for energies that are not get so much used in Gen 4, you can have these kind of things. So it's important to calculate. So here I just add, this is one step when you don't have any borders. So here is the flux I add. So I have initial step, a long step is one class in Gen 4 that say what's happened when you are here and you go until there. Okay, so have your press step, your pause step, and you have your long step. So these are classes that you can communicate and exchange information with Gen 4. So you have the end of step, and then define, pause step, and then you finally track. If you have a border, it's a little bit different. Gen 4 calculate the steps in the beginning, and they will see, okay, can I give the whole step without cross a border? No, I have a border. So it's going to see the flags for the recognition of borders that you define for your model. And then you say, okay, you can go until here. And then I need to be a more detailed because until the border, I need to describe a little bit better the physics. So it's going, stay here. And then he gets information and tells you, okay, now I have a new material or not. It tests it. And then say, okay, it's a new material, so I need to create a new situation. So it's calculate again the step, calculate the step, the post position, blah, 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 and take the step. And when he crosses a border, okay, G4 has one notification for you, G4 transportation. When you have G4 transportation in the code, you say, ooh, I cross a border. So usually you don't deposit energy. If you deposit too much energy in this, it's because your model is not very good. It's because it's compensating the energy the conservative momentum of energy and momentum for this algorithm. So it's going to deposit all the energy at the end of the border. It happens to me once in Gen 4 DNA that you use a model that deposits a lot of energy at the end and the middle has nothing. So you could invalidate this. Today it's not available with this model, but it's the Gen 4 DNA 2 option. In that time has this problem. Okay, it was a theoretical model that was prepared to be in so much small volumes. Okay, so Gen 4 do that. So at the moment, what you need to know that Gen 4 knows how to deal with that. If you need to change it, you need to study a little bit more, because they have. Last time I saw it has 15 ways to change a little bit how Gen 4 describe this border and how we're going to deal with that. So you need to study the code. Usually you need to go to the source code and then go to the manual. It's a little bit different to see. And then here, just to see, usually the accuracy surface is in default, it's 10 to the power of minus 9 millimeters. Then we start to do a describe and what's outside, inside, and we start to do the detailed treatment for Gen 4. Okay? And you can change it. This is the default, but this is the parameter that you can use in your macro, external macro. This is the one to communicate if you want to change it. You can change it by the macro. Okay, this is one of the parameters. So we check if you are in this distance, and then it start to be detailed, especially the, how can I say, the charged particles. Okay, so then the other treatments are the, it's default is true. I put the
Gabriel?
default here. Yeah, oh,
Yeah.
sorry.
What is this yellow region? Just for me to
This yellow
understand.
region is your volume.
Okay.
Okay, you have a volume. And then you have the particle that's crossing this volume. So now we saw in the first one, just a second, so I go back so I can show you. I'm sorry, the yellow region is your volume. The boundary is this line. Okay?
Okay. So this surface tolerance is the tolerance in the border, right?
Is the tolerance the
Of
border.
the-
It's
of the-
calculated for the angle it's coming, so it's calculate the border.
Okay. So what is
Distance.
the geometry tolerance? Is around the particle or something? Because it.
Because sometimes, okay, this is geometric tolerance and surface tolerance. Because sometimes you have fluctuation in the surface. So you can define one unique border, or you can define a surface around the border to increase this. So these are two different things. And then when you come here, you can get, there are several things. I just put a few of them, okay? But let's say here you have this particle that's living, okay? The original point is here. And then after, push inside volume. So you have the possibility to know the angle that you are entering in a volume, leaving a volume, having the energy, and all this information. And it's treated very detailed in Gen 4. For example, here is a problem. What Gen 4 does if you have a, when I started Gen 4 several years ago, you have a lot of description geometry like voxelization. You have voxel models. So the problem of voxel models, you have the vertex, usually in the way using medical physics, you have a lot of particles that crosses the specific point of the vertex. So Gen 4 sometimes got crazy because you don't know if they're inside or outside. So it's get an infinite looping. Now they already have an algorithm to treat that. This is one algorithm that they implemented in Gen 4 to avoid this kind of things. So this is the zero-step protection that you have here. So he can go small, infinite steps until he got something. Instead of defining one step, he's going infinite steps several times until he got out of this line, and then he started processing again. It's avoid this infinite looping. And then, of course, it checks not all the geometrical borders, but the materials. And if are inside or outside, the density of the materials, the energy of the ionization energy, and all these characteristics that you define in our material. Okay? So this is one. You see that there's a lot of things. I'm sorry, it's just 2 hours, so I need to rush. If it's too simple for you, no problem, okay? Just let me know. So what I need to run an application? Okay, I need to have the geometry. It's usually detector. In the examples of Gen 4 is the famous detector constructor class. Okay? You have on this, and you have the physics evox model. Usually you do that in the main, because you are calling the physics that's already done. So you call it in the main code, usually, especially for high energy physics. And then you need to define you call the source, but it's the primary generator action class. So these are the three classes that you need to understand after you start to run in Gen 4. Okay. You can start the virtual machine so you can run something. I can show you, but I just like to show you the main structure of that. So you construct in the geometry, we have the constructor. I used to call define material classes because I have one class with all the materials that I used, and I call it because it's better than put everything in the detector constructor, but it's called in the detector constructor. So in the detector constructor, you create all the logical volumes, okay? Of course, the solid volumes, the logical volumes, and you put it in the proper place, okay? So the material should be there. Then you define the volumes, and when you have to use sensitive detectors, you can implement in other way, okay? Because now you have the native scores in Gen 4 that you can call for a messenger. You can define outside of the code, but if it's recommended for very simple case, okay? Otherwise, you can create the sensitive detector that usually are very fast. And you say at the end, you have a class where you say, this volume is a sensitive detector, and then you create a class that will accumulate and evaluate your data and get with the information of the vertex, the information you want. Okay, but you call it in the detector constructor at the end of the detector constructor. And then you return everything to the world. Okay, aquí I will just let it the coding for you. Okay, we are going to pass to the experimental because I think it's almost at the end and we need to do something. Okay, I put something more. Oh, the physics list. The physics is something important, guys. I'm sorry. But here I add the examples of different physics that you have already in Gen 4 that are very useful for especially the great experiments because you already have something done for you. So to see in electromagnetic physics, you have several models, low energy models, standard models. So which model I should use? Here you see for hadronic physics, you have several models. So which is the best model for me? How can I select that? Depending on the energy you are going to use. So you need to understand the energy particles that you are using, the sensitivity you need to have in your experiment to start it. And then you choose the one that Gen 4 has in that list that I sent to you, a recommendation of physics list. If you want to have a detailed secondary electrons, low energy, use this, and that. So you have this for a starting point. You have something realistic, but you can get improve that with the time. So you can change it. But the recommendation is to go to the Gen 4 webpage and get the information of the physics list. And please use, and now I have it for you, use this thing. This is very good. Do you know this Gen 4 browsing code tree? Let's go, guys. Yeah. Here you can see several different versions of Gen 4. Okay, so it's very nice because if you're not getting used to use the shell command to use that, you can navigate for the whole code of Gen 4, including the examples, and you can see that. And the nice thing here is, if I wanted to go, oh, here is the examples, but if you are going to see the physics, you just go physics list. Oh, come on, my browser is not helping me. Physics list. Okay, and then you have the constructors and the lists. So you have the constructors here, and then your electromagnetics, let's say, of course, and then you include in source, and you go here, and you can see all the coding of the physics list. What is, I'm not getting DNA because, oh, you see, this is just DNA physics. Okay, but let's go. Livermore not polarized. It's one low energy model. So I can go there and I can check all the classes and models that are invoked. At least I can understand what kind of multiple scattering has been invoked. Here are the classes. And these things here are the parameters that I'm talking to you about. The parameter that we use to just for verbosity. Verbosity in Gen 4 is the thing that the code shows to the level of information that the code shows to the user. It's very interesting to play with that in the beginning. So you have that, and you have the minimal energy for set for some different models. And the skin, for example, is skin multiple scattering type limit lateral step. These these three things here are related to the recognizing of borders. So you can check here all the information. If you go down, not going to spend because it can take a lot of time, you can see all the process and the models that are being invoked and the in energy range that we are applying this. So it's not difficult in Gen 4. Of course, you don't need to understand the implementation, but you know the model you are using, and you can check what you expect from this model. This is important in Gen 4. This is important in any mode. And when you have a tool that's closed, it's difficult to understand that. But here, you can have it very easily, even the secondaries. So you can have all the information here. This is something that I think it's important. When you, why are you looking at me like that? She's looking at me like very upset. So here, it's small. I know that you cannot read here, but I put for you to have in the future. So you can go here and you can check. And if you put in Gen 4 web page, physics constructors and physics models of Gen 4, you can have the main information. Then you go to the source code. It's the best way. I think so. And the source. How we can define the source? The source is the primary generator action. So you define first everything about this particle, what particle it is, what the momentum direction, position, time, and everything else. And then you define, you generate an event and define the primary vertex. So it's a command you give in your primary generator action. And then after that, it's going to create a structure for the tracking with the whole complete information. So you see, Gen 4 is different for the other things that you are using because Delphis and the other stuff, you need to create the physics sometimes to get it. In Gen 4, this physics for transportation, these conditions, already done, but you need to be sure what are you invoking, what class and model are you invoking. This is very tedious in the beginning, but this is very nice at the end. This is the nice thing. So here is just to understand, okay? I put here an example of coding for you. All the examples has this, okay? The most important thing is that when you get for this command, it's the last one you give in your class, you need to have defined the other commands. And usually you have the momentum direction, this is a particle, you create, how do you do that? Okay, you create the particle definition for one specific particle that you can call even by the number of the PGA, or you call for the name, whatever you want. When you have this big detectors, they basically they code the ID because it's complicated. Then you create the table for this particle, you define the momentum direction, you define the momentum, general momentum if you want, but you can put everything in the momentum direction. You can define the kinetic energy. If you need the time, you can set up the global time for starting the point. Okay, and then you can polarize and do other things that you have in the G4 particle generator. You have the class with all this information. Then you create a vertex, and then you send this vertex. Then are codes. If you are trying to, if you do not change, it's all the same, monodirectic, monoenergetic, and everything, blah, 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 you can put everything in the main, in the constructor. Otherwise, you need to put in the last class at the end with the random generator that you need to use for that. And I'm not going to spend much time, but I put more information for you. But I'd like to use these slides because some people asked me about that today. So I add this one. So how we use the random generator to define one process or define something inside. So how we do that in Gen 4? Well, I took something very simple. I took 3 processes, okay? And for one specific energy in the table, I got these cross sections, okay? This is something. So what Gen 4 do in this case? When I got a particle here, I need to define what's going on next. So Gen 4 take the sum of all probabilities in these cross sections, and it made a probability in 1. So it create extension and probability of 1. So you sum all of them, you have these in bars. So you take the bars, you keep the probability, you take the cumulative probability, and you put it here, the information of boundaries. So just for use the random generator, okay, and define one number between 0 and 1. Just that. And then depending on the number, this represents the probability we can get. In this case, we got this number. So this is between the first level. So okay, it's going a coherent effect. If it was another number, so it's uh, randomic distribution and it's an homogeneous distribution, you can have the proportion about the different size of the regions that you are interested on. Okay, the main idea is that. Then you do that, and then you can use this process for the other characteristics that you need to define by random number. Okay? So you see it's a lot of calculation for each step we are doing. And then, of course, here I put all the process in Gent4 that are you have to compute all the cross sections. So every time you download Gent4, you have that lot of libraries, a lot of libraries. These libraries are specific for specific regions and particles, so you need to download. You can use only the ones that you want, but you need to be sure what space are you using in the secondary particles you have. But then you have the total cross sections, you normalize it, you generate a random number, and then you create the space phase and define the location you have it. Here I just put some code for that, but I think today is not the time to do that, so I'm sorry. And here, okay, this is the main thing. Now we are going to play a little bit. But here I put some, if you go inside here, you see that I have links. So here you can download the texture for each one of the experiments, okay? The official ones. Yeah? Hmm? Yeah? Ah, okay, so I need to see that. Thank you. You share one. Ah, okay, okay. I'm sorry, because it's a lot of them is made mistake. I need to check my code, so I check it. Okay, I'll check it. Thank you. So let's go have fun. Finally. So the ones who has the virtual machine, let's play a little bit. I'm sorry to doing that, but you see, this is just scratching the surface to understand how to deal with Gen 4. If you're going just push and press the button, it's a problem. So it's important to understand a little bit. Oh, I'm putting my own code. 1, 2, 3, 4, 5, 6. Ajuda. Tela cheia. Okay. So here I will do in the simple way. So I open the terminal. Okay? So if you open the terminal and give an ls, we'll see that you can find Giant4 11.4.0. It has another version, but I had no time to update the machine. So you have this. It's 11.2 now. Okay? So here I install the way Giant4 is to do. I install everything in the same place. After I will show you how to do that to a little bit different, as I used to do in the computers of the university. So save a little bit of space and time when you need to find the things. So let's go to do something to make you happy. So if you give a CD and go to the Giant4, I don't know how much of you like to used to have the terminal, everybody, so it's gonna be great. So you go to inside Giant4, and then I made all the subdirectories. The build here is the one that I use to build Giant4. Some people used to delete it. I don't, because if I want to implement something additional in Giant4, I just go there in the directory and I can use the CMake to enlarge it. Okay. Just a second. Up. Oh, come on. It should be Content Plus, but it's not. Okay, this is the keyboard, so I'm sorry. I cannot make it enlarge it. I'm sorry. So if you have the Gen 4, here is the builder, is the way that I go there inside in Gen 4, like they say, the CMake. You know the difference of doing the first the CMake and after the make in the programming? Okay, in CMake, you have the setting the environment to install. So you set your pointers. So when you put the CMake and all the options you want in Gen 4 and you point to one folder when you have your CMake list. CMake list is the code that have all the information about what I should to consider to install Gen 4. And then you do the make. The make is the compilation. Okay, and the make install, you put all the compiled stuff inside of the install gear. So you know where your libraries that were built are. So this is very important you understand where things are, because when you need to change it for, sometimes you need to to point for different places, okay? So here I already have it. And then you can go to the examples, basic ones. Then you give ls. And here you have two different times to do that. Once a time or everything together. I'm going to do everything together. Because I give CH mode 777. That's why it's green, okay? Because otherwise you need to use the root all the time and it's really annoying. It's really annoying. So you can mkdir, you can made a builder here. Why I made a builder, okay? Some people doesn't like to do that. But when I made a builder, I can guarantee that all the constructors, all the compilation stuff are in the builder. So if I need to delete it, it's easier. Otherwise, you're going to mix with your example, okay? Just that. It seems to be tedious, but I see a lot of people who doesn't know that. Build. You can give the name you want, okay? I used to give builder. But you can give the name. It's your directory. You can call it whatever you want. So you go inside this, and now we are going to call cmake dot dot. Why dot dot? Because if I see ls dot dot, you see that I have the cmake list. Cmake list is the file that have all the pointers to cmake. You can have just one day just to discuss how to do the best cmake, but we don't have time. I'm sorry. Then you can give this. So now we have one the build here, and you know that the cmake list is in one directory before. So for the example, I just need to do cmake dot dot. Open. Cmake dot dot. Okay, it's going to compile. Now it's going to create all the environment to compile all the 5 examples. So it set the pointers to Gen 4 and all the libraries. And now I give the make. It's ridiculous, but it's not going to be too fast, but in all the case. Now we are compiling. And doing this way, you are compiling all the 4 basic examples. You can do that by doing inside of every B1, B2, B3, B4, create, and do the CMake. You can do that too. It takes a lot of time. The basics is not needed. It's usually when you install Gent 4, it's nice you run all the basics, and then you can take the extended or advanced you want. Oh, sorry. You want to see the commands? Here. Oh, it's complaining. It's the same machine that I have. Don't do that. Let me see. That's why hands-on is so complicated in Gen 4. It doesn't find the CMake. I can see that. Okay. Because you should do. You are in the builder? Are you in the builder? If you're having some problems, I will show you how to do that. I'm going to release your directory, okay? So sudo cgamo. Yes, I'm going to Hive. I'm going to solve here and show you. Just a second. Just a second. Yeah, no, we're not resolving because you don't have the. I'm not doing the sudo because I know it's not going to resolve it. Okay. Okay, let's go. Okay. Then you have the build here. You have nothing. Should work now. Okay, so that's the thing. When you use to do, you are trying to go to the environment like super user, and you are not super user. I don't have the dot root bash rc defined for that. So what you should do now, I'm sorry, I thought I was, you need to go back. You see, I'm going to go back one by one to see where you can to the main directory. Then you will see Giant4 here. Your Giant4 is not green like this, correct? Okay, so you need to give the follow command, okay? chmod to release. 777, release everything. -r, Giant4. Okay, I'm sorry, you need to give the sudo before, actually. Control C, I'm sorry. You need to give the sudo. Sudo. This is the command. Huh? Volta to primeiro, to the main code. The weird thing is I did it before I release it. I don't know why the machine didn't save it. With the PDF in the 11? No, no, no. More? Okay, now yes. Now you can give the code. Sudo. Yeah, I know, but I am old-fashioned. I am old-fashioned person. Yep, let me know. Oh. So now it calls you the password that you know 3 4 5 6 1 2 3 4 6 4, and that's all, folks. Now when you do that, it's gonna be like this, and then you can compile. Okay, so let's go to the Gen 4 example. Basic, it works, you know. Build here. So you can give the cmake dot dot. When you do cmake dot dot, you are looking for the cmake list before. So this dot dot is pointing wherever your cmake list is. If you wanted to spread around your computer, it's your choice. I used to put everything together so I know what things are in which part. So that's the only one thing. Okay, then you do the make, and when you finish the make, you will have this. Okay, so now we could run the Gent 4 examples. Okay, so go B1, B caps 1, CD, and then you give ls, and you have this information. CMake files, CMake install, all these things were built, and of course the macros and this out and input were copied from the original B1 example. Okay, so now how to run. The first thing, we are going to see something weird. Example B1. When you do dodge slash writing source or to run it, okay, and then you run. Then it's not gonna run anything. It's gonna wait for you. And it's open a very nice visualizator. I will show you what's going on here in the code, okay? So when you do that, it is key that using the OpenGL of your computer to have one very nice, easy way to interact with Gen 4. Okay, I'm sorry the ones that you have already used it, but it's the way to do in the beginning. So if you wanted to see anything running in this way, you can do. Yeah. The previous command? Oh, it's just, I put it here. Dot slash example B1. I won't forget it, this one. Capital, oh, the B capital, okay, B1,
Capital letter.
B1. So when you got here, I go with you, just a second. I'll give you one action to the other people, then I go there. So what you can do now is interact command lines here. That's very nice in Qt. Because if you're a user that's not get used to know all the codes, you can put like, I want to run some history, some events. How can I go? I saw run, and then you see, it's open the options with run for me. So I can see the option. I don't need to, in the beginning, to know. So you run been on in our option. So we are going to run beam on. 1 point, and I can take the number of particles. Oh, I did a space, you see? That's why I don't use glasses when I programming. It's for long term. So you can see, there are some problems here. You have too much information in this. Because I will show you where you can get this information, you can change it, but you have this a lot of things right in here and stuff like that, so you can move this. But you see, what you see in here in the beginning, let's try to make an improvement here. What you can see here, what are the red particles and the green ones lines? The green ones are usually neutral particles. In this beginning, there could be photons. And the red one usually are electrons. But you can choose the color of your particles. This is the tracking information. Okay? Everybody could get this? No? What is the problem? This is missing library for you? Hmm?
In order to be able to run this, you first have to run this line.
Ah, okay, yeah, because it's... Ah, okay, it's missing for you, okay. So you, of course, you do this one and then you do the make. Here you say, okay? Oh, sorry. You have the CMake, dot, dot, and then the make. And then you create this one so you can run it.
Question.
Yeah?
Because when I try to do this make,
I'm going there to see. When you have an error, that's why the problems in hands-on of Gen 4. Just a second, because I cannot see that. Okay? Okay. But these problems here is that because you didn't... Okay. May I? Yeah. Cha. Okay. Okay. What we're trying to do here? To run the example? What we're trying to do here? You are, but it's not here. That's the problem. You are in build here. You already did this make. If we try to do again, it's going to be a problem. So we need to go inside here and then run the example now, or remove everything. Okay, this is something, people, it's very interesting, the question. This is something, when you are using Gen 4 in this kind of make and CMake things, after you do the CMake and make, okay, if you have a problem on setting the environment or it has some errors in the path or CMake, you need to delete everything and run it again. Otherwise, it's going to take the memory of your computer. So you are taking the wrong pointers, okay? Sorry, I forgot to say that. So if you are running that, and when you need to redo the CMake, because you do that. You use the CMake to set the environment, the make to create the environment. You just install if you need to install something, okay? Otherwise, you go to run it. Usually in the examples, you do that. Few examples are not like that. So what you should do that? When you change, for example, in your code and you create a new class, you need to remove everything and start the CMake because it's not going to find your new class because the pointers are already set it up. If you change something inside your code, you just need to make clean and make again. Okay? when you're installing, you get errors in the CMake, you need to delete everything and do again. Okay, otherwise it's gonna take the wrong error, the same error path before. I'm sorry, so let's see how we can, what information you have to do that. Because usually, you see, it took a lot of time. It takes a lot of memory. So when you need to run the production, we're not going to use this. This is just to see what my geometry is okay, if the tracking seems to be okay, to do something nice to show people, but it's not for the production. For the production here, you are not going to do like that. You close it. And here, in this example, we have something as, in all the basic example Gent 4, we have the in file. So this is kind of a macro that we're preparing to talk to this code and give the information for running without any visualization. So if you do that, it's going to run something. And of course, if you have something to compare and you have the output, there you have the dot out. Comparing the results is not going to be the same because the seed is not fixed, but should be similar, the information that you got. Then you can see, oh, my installation is okay. It's running, at least. Okay, let me show you something. You can do that for the other examples, please. It's not going to run one of them. So I would like to show you that because it's not a recipe. This way of doing things, it's depend of the make code. That's what I want to show you. Because I can call this whatever I want, C++. So if you go to the basic for and try to run it, it's going to be an error. I'm sorry, I know this is very basic, but it's the way you can do that. So if you go to the B4A, okay, if you go to B4A, because you have several B4s, and you try to do that, dot example before, example before in. What's going on here? Why it's not falling? No, no, no. No. Ah, sorry. This is it's me being me. Okay, now it's the error that I was expecting. This I know. So here you see there is some variables that you can use in your running code to talk to this. And to run with this thing, I need to use -m. So this is a way to say to the code, you see it's going to enter variables and I can not put it in order, but I can put whatever I want since I notify. So to run this one, I need to do -m. And now it's going to run. So the thing is, it's not something press buttons and stuff like that. You need to think a little bit. So when you need to know what's going on in the examples, it's very obvious, but you need, oh, you have a root file, so you can play with that later. So if you go to the main of the examples, so you go here and you have the README files here. Oh, come on. Sorry, my computer is getting crazy. VI, README. So you have one general view of each examples. It say the geometry, what it's counting, why this example of building for teach you. So that's why the basic examples are, so you can understand how things need to be done in Gen 4, the basic things. Then you can get crazy later, but you need to understand these ones. And then, if you have more details, you go inside of the main directory and have a second README file that have how to run, specifications of each part of the code, so you can do that. Okay? First, you need to understand how to run these ones. And then you can go to the other ones. You need to understand this. Other thing it's important to check. Let's take the basic one, B1, VI example CC. So let's see a little bit the code. So this is something important. I'm sorry, but you cannot make it. So you have all the information. So here, sorry, you will start, we have the new space for B, and you start your main code with two variables. So these two variables are argc and argv. Argc is the number of things that you put in command line. Argv are the variables. The first one is executable, is not variable. Okay, this is the only one way to check it easily. Then what you start? You start creating your executive UE to talk, and you initialize that with a null pointer. Okay, so and you start with the argue1. If you argue1, it's going to run the kit visualization. So it sends you to other code. Okay, otherwise here it's commented out, so it's not defined, the seed engine. So you have defined the precision to output. Oh, this is important, the precisions of the output verbosity of Gent4. Sometimes people use, and I used to do that in my courses, take the verbosity of Gent4, the tracking of Gent4 used to give to you to create the deposit energy in detectors. And sometimes it seems to violate the energy conservation. It's because of when the Gent4 output, not here, but the Gent4 output, the native, it just put two floats. So you have some problems because it's trunking the information. So you lost a little bit of the energy every time. So you can have this idea of you have a problem. But if you make your own verbosity with all the floats, you see that's conserving the energy. This is important because sometimes people get a lot of time thinking about this problem. Okay, so you auto run, you create the factory of run manager, or say this is the guy that's going to create the structure, and you start the running. So the run manager creates is created in the constructor, and at the end is the last thing that we're going to destruct in this code. And then we initialize what? The geometry. So we need to initialize our geometry. You define our physics, and then I show you the classes. I'm sorry, it's already time to finish? It's in time, ain't? Yeah, okay. Then you have the physics, and then you have this class. Set user initialization, action initialization. This class is important because if you don't have this class, I will show you the class before, but if you don't have this class, you cannot use the native multi-threading in Gen4. So when you have your stepping action from the user, all the class that the user need to be initialized by the user need to be initialized here. And then you can control the threads. Otherwise, you cannot run it in a multi-thread, just in single thread. And then here, initialize the visualization. Then you have the control for, so I'm saying. Okay, so you see, if you don't have anything, okay, if you don't have the UI, it's gonna be here. If you have the UI, it's gonna be, and look, so if you don't have anything set before, it's gonna be here and execute this macro. Okay, so that's why it's opening. It's not native. It's programmed to do that in the main code. Okay, then you start here, and then of course you delete everything, and that's done. Okay, let's see how it goes a little bit in the example 4. Just to see the difference, okay? Oh, come on. And then so if you go in the example 4, just to see the difference, why I should put the M there. That's the thing. What is so different on this implementation? These are made for the user. He put that because when he starts to read the argc and argv, it search for some pointers, and after this point, it's expecting something to read. So the best way to do that is this, because if you just read in some order, if a person put the things in the different order, you don't know it's wrong because it could not crash your computer. In this way, you know exactly when I put the minus m, the next one is this one. So you can do that for several things. And when you use multi-threading, sometimes you need to start some classes in the main code. You need to initialize that, then the threads can be calculated properly. Otherwise, you can just initialize one thread and the other be a little bit different, and then you can have some problems. So you need to understand which classes should be like that. So we need to understand that. Okay? So just to show you the last example, then you can show you some implementations, but let's go to the B one again. And if I give you ls minus la, I used to be a uml, but I prefer to show like this because I think it's more realistic. Okay? So here we have some information. We don't see the build here because you build it in another place, but the main example has the CMake list. It's extremely important. Without this, you need to use the compile, the GNU. It's a little bit different, the compilation. Then you have the main code. Here is the input, the output that's not used for run, it's just for comparison. And then you have the GNU make file. If you're going to use the GNU, it's not our case, you're not evoking this class. Include and source. Include is the header of the classes. Source is the source code of the headers. And then you have a README, that's very important. Visinitialize and vismac. So let's start for the structure of this code. Okay? So ls minus la. Sorry if you don't like this, but I think it's the best way to do so. Okay. I put it differently so you can check the different codes. But here you have, these are the classes it was defined for this experiment. Okay? So we have the detector constructor who has the geometry, the materials, and the sensitive detectors that you have. You have the primary generator action, has the primary source particles and its information. Then you have the event action. I show you it's a class that you interact each event to get some information. You have the stepping action. Every step I can interact and get some information from my application. And you have the run action. This one is made by the user. Event action, run action, primary generator action, and stepping action are all made by user. So you need to program that. You can get a Frankenstein for other codes, but it's important to understand your Frankenstein, okay? And of course, you have the similar. In this case, you have the similar in the head files. So the definition of your variables. Okay, so let's see a little bit detector constructor. I'm sorry if I think you should be more exciting, but that's the way of programming. So it's so weird when someone tell me, I would like to see how you work, as I work like this. Okay. So when I have some, first thing, read the specific README file of the example. Then you come here and check a little bit. So what you have here, of course, the first thing we need to create is the world. Is the universe that contains everything. So here you have, you see, they now use the auto. I'm a little bit afraid of this auto. It's very automatic, so you need to do something, you need to be careful. But if you're doing the basics, auto is fine. It will select the variables and some characteristics that are important. So you create the solid world volume. This name, you give it, is your son. It's your problem. Okay? Now you I create a Giant4 box. So I have a box. So Giant4 has several geometrical volumes and have several ways to describe different volumes. In the manual I'll show you before, you can get it. In the sensitive volumes. Sorry, the sensitive volumes chapter. You have one just for the solid volumes, okay? Then, because it is a box, I need to give, of course, a name for that. It's for every volume. This is the name of the volume. Then I need to define the half length in 3 dimensions. Half-land. Geant4 generally creates the volumes in the middle. So always you think that you are in the middle of the volume, okay? Then you create the left-land for each situation. Then you say, okay, I have this thing, so I need to put something in it because Geant4 needs a material. So you create, you give the logical volume, it's create a logical volume, give the name of that, give the material of that, it is created behind, I will show you, and then you give a name for that. Here, I don't like too much because sometimes they put the same name, so you can be confused with what kind of thing you are evoking. I used to have my own way to do that. I put everything in caps here, first in caps here, and everything in low letter here. So I know exactly what I'm evoking. So I don't have problems later. It's a little bit tricky in the beginning, but it's best to the traceability of your code. So after you put, okay, I have this thing of this side, I have this material, where is it? And how it's in the universe. So I make the Geant4 placements. So here I put null point or 0, it means that it has no rotation. If it has a rotation, I need to put the angle for the rotation and the axis of rotation. Okay? You can compose different axes. Then you have the 3 vector of the position. It's in the middle of the sun. This is the mother volume, so you are not going to do anything different. So you call it, oh, who is going to be placed here? The logical volume world, this guy. Okay? And then you say, okay, who is the mother volume of that? What is the mother volume? The model that involves other volumes. So this is the model of the model. This is the world. There's nothing after that. So in this case, you put a new pointer here. You say to the Geant4, you can just have one model volume. If you have 2, it's going to be crashed. Okay? So hey, it is a model volume. So you have a Boolean operation, yes or not. If you have more volumes with the same characteristics, you can give copy number of difference. This is the way they find the parallel geometries that Geant4 do. And then you check the overlaps. Okay, you can put true or false. I used to put true in the beginning, so it's very easy to check everything. And then we're going to put things inside of this world. Otherwise, it's not funny. Okay, so you create again one envelope. This is a box. Again, give the dimensions, give the materials, you give the position. Okay, it's in the center of the world, but now it has a mother volume. It's important that if you're not in the world, you need to give the mother volume. Otherwise, it's going to crash your simulation and segmentation fault because Geant4 defines the inside and outside volumes during this logic process. Okay, so you need to define the mother volume. And you can do that for several stuff. One thing that you need to be careful on here, if you're going to rotate one volume, it's going to be rotated in the center of the mother volume of this guy, not in the world. It's inside of other thing, and when you rotate the mother volume, you rotate everything inside about the mother volume. So you need to be careful when you choose the mother volume for your applications. So here you have several shapes and stuff. Okay, here you define. You could put this as a variable in stepping action, but here they create a scoring volume nave logical shape 2. So this guy here is the guy they are using as a detector. They are just counting this volume, and that's all. Okay, so just to show you a little bit more, so you know, going to leave because it's just few people that start here. So it was very tedious. Source. Let's try the stepping action. When I say the stepping action, it's the moment I can get information for the vertex and the points of information, tracking and stepping. Okay, so here we have the magic of the detectors. If you are building a detector and not using the sensitive detectors that you are creating, different stepping action in your heat file. Okay, sensitive detector file. So here, every step, it's gonna be initialized, this one, okay? And it's, so you create the creator, you create the user stepping action. So we're going to say to this one for the moment, okay, you have a constant that detects a construction, so I create a pointer for this. So I use the information for this and I create scoring volume. And then I say to that, I will count everything that's in that. No, I just will count things that are in the scoring volume when I doing this kind of things. I could don't do that, and I could come here and say my scoring volume is this one. It's gonna be the same. Not make any difference. But you can do something very fancy. You can do this. Okay. Then you say, okay. So what I'm doing that I'm getting the volume and say where I am in my tracking. Which volume is the volume that I am in the moment? Every step I do. And then he say, okay, if it's not the scoring volume, I leave it. If not, I will take the total energy, okay, and add this stepping energy deposit to the event action. Why? Because when you are counting, you need to count by event, not by track, by stepping. So you send every step to the event. At the end, you sum. This is the energy deposit by this history, and you have the number of particles by adding one at the end of this track. So you can continue getting the proper statistics of the call. This is a very step by step because you can do that for sensitive volumes automatically. But it's nice to do that this one day by hand. So I'm sorry, I know that you are tired, so I'm going to stop here. Okay, because I see that everybody is tired. But if you have any questions, you want to install Agent 4 or you want to have any specific questions, I'm here. I'm sorry this is very simple, but it's something. So if you have any question, everybody wants to go home, I think so. Bye. You are hungry? Oh, it has